All right, we're going to use what we know um, to look at derivatives of all exponents. We did some hand wavy from this, so um, we'll try to update our hand waviness. So we're going to look at a function a to the power of x. And we're going to ask ourselves, what's the derivative for this? What we're going to do is we're going to make this our replacement for the function. Because notice e to the natural log of something becomes whatever it is, because they're inverse functions. We'll have to restrict ourselves for a being greater than 0. That's okay, we do that with bases anyway. And if we apply our rule of logarithms, we're going to get ex times ln a. So now, if we let f of x equal a to the x, and we're going to ask for f prime of x, or our derivative here, that means we're going to take the derivative with respect to x of ax, which is the same now as the derivative of this, because we showed their equivalent. And now we'll use the chain rule. So what we're going to say is we're going to say this is e to the u, where u is equal to x ln a. So the derivative of this is du dx times the derivative of this here is going to be eu times du dx. Had to think for a second here. And du dx, right, because eu is its own derivative, right? This derivative of this thing with respect to u is itself, times du dx. And du dx, well, ln a is just a number at this point. So that becomes ln a times x, so ln a. And so this becomes the derivative of itself, so e to the x ln a times du dx, which is ln a. But this is what we started with. And so we get a to the x ln a as our derivative. And so, as we've been saying, as one of our derivative rules that we kind of memorized, the derivative of a to the x is equal to a to the x and the ln a. And we saw that when we looked at the limit of logarithms. We saw a pattern, of exponentials, and we saw a pattern. It was that pattern that made us choose e to the x as being the special case. Let's now look at what happens with any logarithm. So we're going to look at log base a x. And we'll make this our function. And we'll have to remember the change of base formula. So we're going to say that this thing is equivalent to any other logarithm base that we want. And the logarithm base that we want is usually ln. And so the change of base formula looks like this. Now what we're able to do here is, if we take this log a of x and write it in exponential form, that's the same as a to the y. So we're asking what this is, what power does a equal, what power of a gives us x? And so here we're writing that out. And if we solve this, we'll take the natural logarithm of both sides. Of course, I write it out weirdly, as I always do. What we want to say is, if we write this in exponential form, log y equals log ax is the same as saying a to what y equals x. And this is the form we'll use. So if I'll take the logarithm of both sides, use my power rule, solve for y, we get the change of base formula. And this can be any logarithm. Notice this was the part I applied. I chose the logarithm. We tend to choose natural log. So we can rewrite this in terms of natural log. So if we want to find the derivative of f of x, or we're going to find the derivative of log base a of x, that's the same as finding the derivative of the natural log of x over the natural log of a. And we're going to give ourselves a second here to realize that this is the only thing that has x in it, and this is a number. So we're going to pull the ln a out forward, and we're going to do the d dx of ln x, which we solved at the end of the last lecture. And so this is 1 over x, 1 over ln a, 1 over x, which we tend to see as this. And we do get a weird limitation here now. A cannot be 1, because the natural log of 1 is 0, and that would give us a division by 0 problem. So we can add this to our banks of derivatives. And we've built up our derivative tools. All right, let's look at how we can use this to our advantage. So let's do y equals, and this happens a lot in statistics and probability. We get some really nasty integrals and derivatives that you have to do with things being multiplied together, because probabilities multiply. And if we switch to logs, you can turn them into additions because of how the log rules work. And so you'll see that we do that a lot in some specific fields, is we'll let logarithms do the work for us. And so x will have to be greater than 1. We're going to choose the things coming through. And what we're going to do here is we're going to use our power rules to take this nasty set of multiplications through. We could use the quotient rule. We could do a product rule at the top. There's a lot of bookkeeping to do. We're going to preload our bookkeeping because we're going to take the natural log of both sides. And this allows us to use our rules of logarithms. So, log x times y is the same as log x plus log y. Log of x divided by y is the same as log x minus log y. Log of x to a power is the same as the power times log of x, and so on and so on and so on. So we're going to split all these apart. So this is the natural log of the upstairs, x squared plus 1, x plus 3 to the 1/2 power, minus the log of the downstairs. And this top then is the same as the first argument, x squared plus 1, plus the log of x plus 3 to the 1/2, minus the natural log of x minus 1. And we'll do one more writing. we'll get this half power taken care of here. So plus 1 half ln x plus 3 minus ln x minus 1. So I've taken a whole bunch of multiplications and divisions, and I've turned them into additions. And so now I want to find dy dx, so I'm going to differentiate across the whole thing. And we get some chain rules we have to keep track of, but it's not that bad. This is going to give me 1 over y dy dx because of the implicit derivation. This is going to give me 1 over x squared plus 1. But it's a chain rule, so I have to then multiply it by the derivative of this, which is 2x. Then I'm going to get 1 half 1 over x plus 3 times the derivative of this, well that's 1, minus 1 over x minus 1. And then I will multiply both sides by y. And we've got the beginning of the form of an answer. We could try to clean this up a bit, and I think the only thing I have to plug back in is remembering my original y was this. So I'll do that now. I'll plug in my x squared plus 1 times x plus 3 to the 1 half over x minus 1 times 2x x squared plus 1 plus 1 over 2x plus 3 minus 1 over x minus 1. Close my parentheses. And we got our derivative. You're welcome to play with it in the other direction to try using the quotient rule. I find this bookkeeping easier because I've done a lot of logarithms, right? Computer science. If you have to put things into a computer, additions run faster than multiplications. And you can convert your functions from logs at the beginning and at the output, so any delay in that is only 2 calculations. If you're running on millions and millions of pieces of data, that speed increase that you get from changing everything to additions is valuable. And so a lot of times in computer science, we run in log space.